circuit in electronics, because electronic devices operate off of DC, right? And we plug into Alabama Power. So what advantage does AC have over DC? Yeah, we can transmit it. So we can step it up so the current goes down to transmit that power, and then we can step it down for safety. Another thing is it allows us to, in what we call induction. Y'all understand induction? What are we required for induction to induce a voltage? What do we need? Did we go over that last class? Well, we need a magnetic field. I don't necessarily have to be a magnet. It can be an electromagnet. We need a magnetic field, we need a conductor, and we need motion. Well, AC produces everything we need. So when we put current through a conductor, I showed you my electromagnet, right? If we put current through a conductor, it creates a magnetic field. All right, so there's my magnet. And okay, so it creates a magnetic field. But it builds out and stays at that one potential if it was DC. Well, what does AC do? AC collapses back in, reverses direction, then it goes back out. So it produces motion. So if I bring another conductor in close proximity to this conductor, it will induce a voltage in it. Now, what determines how much voltage we induce is the number, is how we couple it. We got to have real good coupling. So that's why, let me bring up my camera. That's why on these magnets we don't use regular wire. We use what we call magnetic wire to get a real good coefficient of coupling. And then we wrap this around metal to concentrate the field. Now AC uses laminated metal, so I don't know if we can see the lamination on this or not. They covered up. Trying to see something I can end it up with so we can actually see the core. Now AC uses, you can tell a transformer, we can't use regular metal. So on this one, I just wrap this around a chunk of metal. This is just nothing but a bone. This is magnetic wire, because if I use insulated wire like this, we get very poor coupling between the actual conductors because the insulation is so thick. Does that make sense? So we use special magnetic wire. The problem with magnetic wire is insulation is so thin that if you get it real hot, it'll burn that insulation right off there. And then you have shorted transformers, shorted motors. So what I'm doing is I'm going to take this, we call it a mu shield. The purpose of this thing is to keep the transformer from inducing a lot of stuff around it. But I'm going to take this off and let y'all look at the actual core that concentrates the magnetic field on AC. The problem we have by on AC trying to use a piece of metal to concentrate the field is that if I use a big chunk of metal like that, that's a conductor. And AC would induce a voltage into that conductor, and it would act like a short circuit. So the transformer would become extremely inefficient. We don't want this metal to be a conductor of electricity. We want it to be a conductor of a magnetic field. So what they do is they come up and they divide it into hundreds of little old tiny plates, and they insulate the plates from each other. So that way the little current, we call them eddy currents, that's induced in this plate does not combine with that one, does not combine with that, and does not combine with that one. And it turns the core to be very, very efficient. So if you looked at an AC motor, you'd see that the poles that actually concentrate the field are what we call laminate. Does that make sense? You understand why? So what this does is now the core is not acting like a conductor of electricity. It's acting like a chunk of metal. So the fields in each, the magnetic fields can combine in each plate, but the currents can't, right? Does that make sense? So this is actually a transformer. So this right here would make a crummy transformer because it's got a solid metal iron. But if you look in the top, you can probably see the two windings. So you got a secondary, we got a secondary and a primary. Now the secondary is the part of the transformer that points toward the load, and the primary is the windings that point back toward the source. And what determines whether it steps up or steps down is the turns ratio between the primary and the secondary. So if the secondary has less turns than the primary, it will step the voltage down. If the secondary has more turns than the primary, it'll step it up. So that's what you could do. You could measure, if you could count the number of turns in the primary and the number of turns in the secondary and get that ratio, then you could see if it was a ×2 transformer or ×4 or whatever, just by the number of turns ratio. That makes sense? So you can look, if you can look down into it, those wires are wound on top of each other. The high current side is going to have the big wires, and the low current side, or the high voltage side, is going to have the small wires. Y'all understand why? Because the high voltage side requires less current to produce that power. The low voltage side needs more current to produce that power. So transformers seeing power through, what it changes is what? Is the voltage level. And if it changes the voltage level to keep the power on the primary and the secondary the same, then the current has to change. So the current in the primary and the secondary is going to be different depending on whether we step up or step down. So normally, if we come up and do most power supplies, we usually start off with a transformer. And what does the transformer do for us? You can't say it steps up or steps down. It's going to set the output voltage. So if you need more out than you put in, voltage out, then you're going to use a step-up transformer. If you need less out than you put in, we use a step-down transformer. Now, normally, if we're going to use solid-state devices, they can't handle a lot of high voltage. So normally we step it down. That makes sense? I mean, even in your car stereo, you're looking at, if you got a power amp, it's usually plus and minus 80 volts, which gives you 160 volts difference, right? You understand that? So this is normally what we kind of look like. If we went straight through, we would start off with a what? With a rectifier, but this is what we talked about the other day. Normally what we do is we use a transformer. So the Alabama Power plugs into a transformer. The transformer sets the voltage, right? You understand? Normally it's a step-down transformer. We're definitely going to use a step-down transformer. We're going to use a step-down transformer in the trainer. I'll show y'all because it's wired up for us. And then we run it into a rectifier, and this is where we're going to start out first. That's where we're going to start off with. So what we're going to do is we're going to use a check valve. Just about all fluid powers or things that flows have check valves. And y'all know what a check valve does? Only allows it to flow in one direction. Hopefully your house has a check valve in it. So that way if they cut the water off outside, all the water in your house won't drain back out, right? You understand? Your fuel pump on your car probably has a check valve on it, right? You understand? So we have check valves in fluid power all the time. Well, in electricity, our check valve is what we call a diode. So a diode will only let current flow in what? One direction. Now, of course, we teach electron flow. What's the symbol? Shift this up a little bit so I can get to my PowerPoint thing. I hope I can. Oh, let me start my slideshow, sorry. So VPIC out would be equal to 5 volts minus 0.7. Or we get 4.3. My DC average, DC, it's just volts DC, even though it's an average. DC is always an average anyway. Would be 4.3 divided by pi, 3.14. What do we got? Would this be a positive or a negative? Here's my source over here. So this would be a positive supply because the anode is pointing towards the source. Okay, you understand? So if I looked over here, we would have this over here, only 1.5, well actually it's going to be VP. It's going to be 4.3 volts P, right? And of course, but we're not going to get peak work out of that, right? You understand? You're going to see V peak out with an oscilloscope, but you're not going to get V peak work. Does that make sense? Yes or no? Because it's not, first of all, we got 0 for half of the cycle, right? You understand that? And then plus the sine wave is not varying linear, it's varying in a sine. Just trying to see if I had a diode up here. I need to bring my diode. We use a function generator. I'll bring it. I don't know if I got a transformer out here or not. I'll try to keep one out here. Dang it, I closed my camera out. So here's the diode, right? How do I know the cathode? Yeah, it's got the line on there, right? So let's make a negative supply. So I'm going to turn this toward my source. And then I need a load. So I got a 1K resistor. What's the color code for 1K? No.
Brown, black, red.
No, black, red. Okay, so here's our circuit. Brown, black, red resistor. Here's the, we're going to come over here and what I'm going to do is, so I'm not going to use, this is my DC power source right here. I'm going to use the function generator, which is pretty easy. So we'll go ahead and set the frequency down to about what we would get off of Alabama Power. Hopefully we're going to get 60 seconds. Looks like it wants to go that way. Okay, we'll go. That's good enough. Okay, and I'm going to come over here. By the way, an oscilloscope, a meter, your black lead is a common. It's meter common. It's not circuit common, it's meter common. So it's what you measure your current relative to. Everybody understand that? On an oscilloscope, this right here is ground. So on an oscilloscope, you cannot probe the black lead anywhere you want to. So as soon as I put this black lead from my function generator right here, which is ground, so this is grounded, that means I have no option but to put this black lead on that ground. And then all your measurements would be relative to that ground. Okay. Now this is not going to be a big deal, so I'm going to come over here and do that. Now all of a sudden my oscilloscope's got something. If you see a line like that and it's spread out, what it means is we're making our oscilloscope go too fast. So I'm going to come over here and take my time per division and I'm going to slow it down. And there it is. Now what I need to do is I don't have my scope given the ability to measure enough voltage, just like on your meter where it would overrange, right? So I'm going to come up here and I'm going to put more volts per division. Let me take off the garbage. It looks like it's got a DC offset. Oh, yeah. So there's my sine wave coming in. Now your ultimate goal is to get it as big as you possibly can on your scope and still see it on the screen. And I'm using a control called volts per division. 67 cycles. So now we can measure. I've got it set so we can measure it pretty easy. So we got it on 500 millivolts per division. In fact, let's turn the output up so we can get more voltage out of this thing. And I'm going to try to set it so we can measure it real easy. So now we have it on 2 volts per division. So that's major divisions. Can y'all see the divisions? So I do 2, 4, 6, 8, 10, 12. So I got 12 volts peak to peak. So what should be the output voltage I'm going to measure on this thing? First of all, your scope measures peak to peak. What's the first thing you're going to do? You're going to divide that by 2, right? That gives me peak. So 12 volts peak to peak would be what? 6 volts peak. Everybody okay? Then what are we going to do? Then we're going to subtract 7/10 of a volt from that, right? You understand. That gives us V peak out. And then we're going to do what? We're going to divide that by pi. I'm going to take my meter. I'm going to turn it on. I'm going to put it on DC. What's our voltage? What we're going to measure? Okay, so I'm going to put my meter down on 4 volts per division, and I'm going to come up here and measure across my resistor. So it's measuring about 1.4 volts. Not too bad, right? I mean, good gracious, 1.7, 1.4, that's about 300 millivolts different from my calculated and my measure. Not too bad. I'm going to come over here and get my oscilloscope now, and I'm going to come over here and look at this is a 2-channel oscilloscope. Notice what I'm having to do. We had a guy burn a transformer up. He wanted to measure across the diode, and you come over here and put his meter right there. You can't do that. You got to put this black lead. All the black leads go on top of each other. I'm going to come over here and I'm going to look at, this is what's going on across my diode. So what I got to do is turn on the next channel. Now notice, here's the cathode. I have the cathode pointing toward the source. So we got a watt. Did it measure negative on my meter? I didn't see that. And I don't know if y'all can see the blue. It's slightly less. Let's move my camera and see the focus. Yeah. Notice the blue, even though we're using the same 0, that's not true. Use the same. Yeah, that is 0. That's trigger. Here's channel 1 and channel 2. They're right on top of each other. But can you see the blue is actually slightly less than yellow? And why is it slightly less? Because of that 0.7 diode call. So this is what the load sees. It sees this pulsating DC. Let me move my channel 1 up out of the way. There it is. How would I turn it into a positive supply? Yeah, all I'm going to do is I'm going to come over here and flip the diode around. I'm sorry, I lost my. Put my power source back up, my meter back up, turn it back on. So now the anode is pointing back toward my function generator, and it's a positive supply. A while ago, my cathode was pointing back, and it's a negative supply. And that's all we have to do to get a positive and a DC supply. So this guy here's got a positive and a DC supply in it because it's generating AC. And it's doing it electronically, right? You understand that? So how can I generate AC from, first of all, we convert it to DC. We have a positive supply on one side, we have a negative supply on the other, and now we electronically can control that with our amplitude. And then we're able to electronically control the frequency, and we're able to electronically control the amplitude. So we can use DC to create AC, which is, I think I told you, that's the way your car stereo works. So your stereo in your car, and even your cell phone, outputs AC. But yet our batteries is one polarity DC. So what do? They bring it in and electronically do something, generate a what? A negative and a positive DC voltage, re-oscillate it, generate a negative and positive voltage. And then now it can now it can electronically generate AC for my speakers. Don't ever put DC on the speaker. Burn it up. So we worked out pretty good. So now we should be able to measure about the same voltage. So I'll put my meter back on, but this time it should measure positive. A while ago, hopefully it measured negative. I didn't see that. So about 1.5 volts, about what it was a while ago. We let it settle down. We calculate what? 1.7. That's too bad. I mean, that's only what? A couple hundred millivolts from our watt are calculated to our measure. So odds are the diode's dropping a little more than 7/10 of a volt. Or we measured D peak wrong, but I don't think we measured it wrong. Now, of course, if I measure V peak, if I measure this with my meter, if I measure the output of my voltage source of my meter, so now I got it on DC, I'm going to measure across my voltage source, and it's going to measure what? It should measure pretty close to 0. That's why it's moving around. 60 cycles, the meter tries to measure it. Okay. So what does it mean? Well, it means I'm not seeing 0, I'm just got it on AC. I got it on DC trying to measure AC, right? Put my meter on AC. And it's measuring about 4 volts, right? But that's what? That's RMS. So if I wanted to see V peak, I would do what? RMS divided by 0.707. What do you come up and get? Hopefully it should come up to be 6. Or close to it. Because 0.7, yeah, 5.7, y'all don't understand it, yeah. No, I'm measuring across the actual source, yeah. Should be about 6, right? You understand? 0.707 is just a rounded number. It's actually no, not sine of 45. Yeah, you're right, sine of 45. But if you look at the sine of 45, it's actually 0.707070707. So just like pi, we round pi off a lot because, you know, pi is an infinite number. Well, they don't know. They've never found the end of pi yet. And pi is a non-repetitive number, which means it's never usually fractions eventually will fall into a repeating pattern if you carry them out enough digit. Pi has never done that. Last time I checked, and this was years ago, it's probably 10 years ago, and they had calculated out to 2 billion digits. And Harold on the person of interest said it better than anybody I ever seen. He says, every number that's ever been written is somewhere in pi. So your social security number is somewhere in pi. I mean, it's in there. Of course, I'd hate to go out and try to find it, but it's in there somewhere. I thought that was pretty neat. So everybody okay? So that's pretty straightforward, you know, so what we're doing now is we're taking AC and converting it into what we call what? Pulsating DC. And what you still get an average. Now your DC meter works great over here because it's giving you the what? It's giving you that DC average that we're calculating. Everybody okay? Okay guys, you'll take a break. Few minutes. backboard select data sheets. And what this is the actual spec on the data sheets. And you can see some of the stuff that we're going to be dealing with this semester, all these different devices. And right here, this says this is the what? Three-terminal regulator. This says the what? This is the what? Variable voltage regulator. In fact, we'll actually open up the trainer and look at these. They're pretty neat. So right now we're looking at, I think our lab is going to be on a 914, 1N914, which is what we call a small signal diode, which means these guys are not normally used for rectifiers. They're used for signal handling. Well, let's look at some of the specifications. This is the 4000 series right here that we talked about just a little bit. So let's go ahead and open this guy up, the 914, and let's look at some of the specs we'll run into. So first of all, in a data sheet for solid state devices, one thing they give you the temperature that all the measurements was made in, because we know that solid state changes with temperature, right? You understand? 25 degrees centigrade, which is right around 73 degrees Fahrenheit, right around there, so they can figure that to be what we call ambient temperature. So just about all your solid state devices are going to be rated at 25 degrees centigrade. Then we get into a table we call the absolute maximum rating table. The absolute maximum rating table is not the operating condition. This is the maximum you'll ever put on the diode. So what that means is that if I stay below these things, the device may not operate right, but it won't be damaged. Does that make sense? So it says VRM. Some people call this PIV for peak inverse voltage. This is your breakover voltage for this diode. So that means if you ever put over 100 volts peak, this is DC, by the way. So we're talking about peak. So it means if I put this thing, if I try to make this thing block over 100 volts peak, it could what? It could bust it open. And this is the guy we're going to break over. So this is why we're going to do this as a lab, because that means we're going to have to put over 100 volts DC on this thing to break it over. We're going to break over the 914 on purpose. Then we got our forward current. So what's our value of our maximum current on this thing? Yeah, 200 milliamps. So as long as we don't make it conduct over 200 milliamps, we should be okay. A peak repetitive forward surge current. This guy here, a non-repetitive, so that means usually it's one cycle. This guy here could handle 4 amps. For what? 1 microsecond. It could handle 1 amp for 1 microsecond. So we're going to have to be good. That's why we can't use it on a 60 cycle, because we're dealing with 18 milliseconds, right? Well, we could use it. We just can't get this out of there. What we're going to do is look at the, we're not looking at thermal. What we're looking at for is the operating characteristics, the electrical characteristics. So this is what we want to operate in right here. So it says the breakdown voltage is what? 100 volts. We already knew that. The current, if you break it over at 100 volts, is going to be around 100 microamps. That would be leakage current, but that's a minimum condition. It's probably going to be what? More. VF, there's my VF that we talked about. So this guy depends on its operation. It's going to be around 720 millivolts, which is about what? 0.7 volts. But when we get up to 100 milliamps, this guy could actually be dropping what? 1 volt. Y'all understand that? So that 0.7 of a volt we use is just an approximation. It all depends on the actual amount of current we go. Reverse current. So this is how much leakage current we get. 20 volts. we're going to get a maximum of what? 25, but what's that? Nanoamps, right? At 150 degrees centigrade, which is really, really hot, then that's going to be a maximum of what? 50 microamps. And if we put 75 volts reverse on it, we're getting pretty close. It's going to be 5 microamps too. So we do have current flow in the reverse direction because there is a path for the current to flow to get through there, right? You understand that? But it's not very much. Total capacitance, we're not going to worry about that right now. And so what we're interested in here, of course, is this guy right here. It's 100 volts. Some books call that PIV, which stands for peak inverse voltage, which means inverse means what? You know, so this is what we're really looking at, right? This guy right here. And that's not RMS. Y'all understand that? That's peak. So you need to know how to calculate peak when you put this thing into something, you know, because I might have, if I put this thing across 120 volts AC, then peak is going to be like 170 volts, right? You understand that? And what could happen? Yeah, it could pop it. Well, pop it. It's going to go bad. And the problem is, how's it going to go bad? It's going to either open, or it's going to short, or it's going to become very leaky, which means your reverse current is going to go way up. And that's the problem with it. There's no way. We tried to make transistors bad. We tried to make them bad the same way, and it was really hard to do. Sometimes for testing transistors, so we got a big old DC power supply over there in the other lab, and we were deliberately exceeding the breakover voltages and was trying to short them, and it was real hard to get a bunch of them the same way because they would go bad different ways. Total capacitance we're not going to deal with. That deals with, and this is it. This is the big guy too, the milliwatts of power. So power dissipation on this is what? 500 milliwatts. Yeah, 500 milliwatts. So let's go back and look at the other one, which we're going to do. We're going to use this guy a lot, the 4000 series. So the data sheet actually goes from 4001 to 4007. And what varies, I think we already talked about this, the only thing varies when I look at the maximum rating table, the only thing varies is the what? The breakover voltage. Okay. So the one in the 4001 is breaks over 50 volts. 4002 breaks over at 100 volts. The 4003 is 200 volts, 400 volts, 600 volts, 800 volts, and then the 4007, which is 1,000 volts. This guy, the average rectifier forward current is what? 1 amp. But this guy right here, it's a rectifier diode. That's what it says. So it can handle up to what? 30 amps for one cycle. Now that'll become important later on because when we start adding filters, when you originally charge those filters up, they're going to take a ton of current. And this guy right here would be able to charge that filter up 30 amps because after one cycle, it's going to stay charged up. And we're never going to let it discharge all the way. If we choose the right size filter, it'll never discharge all the way. Because by the time it gets down a certain amount, the next peak is going to pick it up and recharge it. So that 30 amps is going to be fine for this guy here to run a 1 amp power supply. This guy will run a 1 amp power supply fine. Electrical characteristics, this guy right here could get all the way up to what? At its maximum current. This is at 1 amp, that's what it's rated at, 25 degrees centigrade. VF could be, typically it's going to be what? Can y'all see that? About 930 millivolts, excuse me, about almost a volt. It could be all the way up to 1.1 volt. But that's at 1 amp, right? That's at the maximum rating of the diode. So that 7/10 of a volt that we use is a watt. It's actually an approximation, right? Y'all understand that? If I wanted to know the actual voltage drop, then that's going to take a lot of math that we don't need to use, because the 7/10 of a volt is what? Is okay, right? Especially in a technology where our math is perfect, but our components are not. So there's very seldom in electronics that you're going to calculate exactly what you're going to measure. So that's why in DC, y'all remember what you had to do in DC? If you had a 1K resistor, what did they want you to do? They wanted you to measure it. And then when you did your back math, you wasn't supposed to use the color-coded values. You were supposed to use the what? The measured values. Because you were trying to prove, our laws. You was trying to prove our Kirchhoff's laws, and you was trying to prove our Ohm's laws, right? You understand that? But now when we get into these classes, we don't do that anymore. What we do is we take the color-coded values, we use our color-coded values to do our calculations, right? You understand? And we know that our measured values are not going to be the same, but they're going to be what? Close enough so you can tell if something's wrong. Yeah, so if you calculate the output's supposed to be 15 volts and you go in there and measure 5, then you know what? Something's wrong. But if you don't know how to calculate it, if you don't know what it's supposed to be, and you measure 5 volts on the output of a DC power supply, you might say, what? Well, that's good. I measure something, right? You understand? You measure 30 volts and it's supposed to be 15. Maximum forward instantaneous voltage up to there. Maximum full cycle voltage. This is the maximum full cycle forward voltage drop at 1 amp at 75 degrees centigrade. And notice this guy gets into pretty good detail. This talks about what? The length of the leads. A lot of people don't understand that the length of the leads determines how fast the device can get rid of heat. The longer the leads, the longer it takes. Because basically most of your syncing is done by the printed circuit board itself. So you get these big old long leads, then that's going to hurt you as far as just getting to your syncing source faster, right? Or what else is so? Y'all got any questions on this? Maximum full cycle average reverse voltage current. So full cycle average reverse current. So this is our reverse leakage current, and what's that? Maximum 30. If we let it get above 30, it's going to cause problems, but it shouldn't get above 30 as long as we stay below the breakover. 30 microamps, which is basically nothing, right, compared to 1 amp forward bias. So this guy's a good rectifier diode. This is the 1 amp. We call it a 1 amp diode. That's probably up at the top. No, I don't. So data sheets for diodes are fairly easy to understand. But on this diode, a rectifier diode, now on the switching diode, you could get it in what, microseconds, right? You understand? This guy says for what? 1 full cycle, which means we could maintain 30 amps on this guy for 60 cycles for what? About 16 milliseconds. And we're only going to do it for a half cycle, or less than a half cycle, so we shouldn't have a problem when we start charging this thing. It's just that when we originally charge it. And we'll look at the PIV. When we start playing around with next class, when we start looking at full wave rectifiers and charging up the capacitor, charging up that filter, you're going to have to figure out that PIV or that reverse breakover rating on the diode, because it's going to be a lot more than, sometimes it's actually over peak P, and we'll have to look at that. So we okay? So I think the diode lab, though, is built around the 914. And what you're going to do is you're going to develop that, what we call the VI characteristic curve. Do y'all remember that? Yes or no? Basic VI characteristic curve for a diode. Remember what that looks like? Stop this slide. I'll have to bring up the other one. Don't sound like y'all do. Nobody. So what y'all going to do is we're going to draw the VI characteristic curve. So this is basically what a VI characteristic curve looks like. So this is so this is I, and this is V. So my source starts going up. Here we might have 1/10, 2/10, 3/10, 4/10. This is just leakage current coming through the diode. There's hardly anything going on, right? You understand. And then when you get up around 5, 6/10, you should see it do what? You should start coming up, and then it's going to move in a slant. Because now it's dealing with the R of the semiconductor, right? You understand? And that's why they was talking about the VF actually varies. Once the diode is forward biased, the VF actually varies with current. And it's linear too. Now, this is what we're going to do as a class. Because we're going to be using the 119, and this guy, it's not going to break over. You know, 100 volts might be right there. And of course, it's going to be dangerous for us to deal with that, right? So we'll do this as a class. And what we're going to do, and let me explain this to you. So what we're going to do is we're going to come over there, and if you look at your lab, we're going to come over there, and now we're going to put it in this way. This is going to be that little 1N, 914. And then we're going to come over here, and we're going to put a bunch of power supplies over here. We'll draw it as one. We're going to use a bunch of them because our power supplies won't put out over 30 volts anyway. So what we'll do, we'll hook them up series 80. I don't understand series 80. Did y'all go that in DC? Yes? So we'll just hook them up like this. And of course, what happens is their voltage adds together, right? So I think we're going to use 4, which might have to use 5. 4 of them would get us up to around 130 volts. And then what we're going to do is we're going to come down here and we're going to use a 10 gig ohm resistor. Because if I don't break this thing over and protect it, it would burn up, right? And so this is going to be a 10 gig ohm resistor, which is basically an open, but it's there. And what we're going to do is we're going to take our voltmeter and we're going to put it in parallel with it. Now, the problem we have is I'm taking a voltmeter that's got about 10 megohms worth of resistance on the volt scale. I'm sorry, it's got about 10 megohms worth of resistance. No, we're going to use a 10 megohm. I'm sorry. So I could say a gigohm. That would be. It's got about 10 megohms worth of resistance in it, and we're going to hook them in parallel. So when we calculate our current, so this is what we're going to do. We're going to measure the voltage drop across this, and we're going to see it start off real low, and it's going to creep up slightly. So what we're in this little section right here, and then what's going to happen? All of a sudden, it's going to take off. The voltage drop is just going to increase real fast, and then that way we'll know we just did what? We just broke the diode over. And what we're going to do is to measure I. Of course, D is we're going to have 1 meter. We're going to have 1 meter measuring this resistor right here, right? You understand that? We'll have another meter right here. So we use 2 meters. So this is going to be measuring VR because it's going to be reverse bias. And that meter, we're going to use that to measure the voltage drop across that 10 megohm resistor. And then we're going to calculate IR. So what is I equal to? VOR. So if we know the size of this resistor and we measure the voltage drop across it, we can calculate the current flow through the resistor. And the resistor is in series with the diode. And what's the same in a series circuit? Current. The problem is that we can't use 10 megohms when we calculate that current. Why? because my meter is in parallel with that 10 mega ohm resistor. Now, normally you get into a 1K resistor. So let's say I have a 1K and I want to measure the voltage drop across that 1K. And that sucker's got 10 mega ohms. That 10 mega ohms is not going to, we're going to forget it completely, right? You understand? But if I get into a high resistance circuit with a meter, we cannot ignore the resistance of the meter. Now, I'll tell you the story about Dennis Ramsey shutting down number 4 gallon line at US Steel. Was trying to measure the output of a mag amp. The mag amp is a high resistance device, and he put his meter in parallel with that thing and changed the output of the mag amp because he was putting a high resistance, he was putting it across a high resistance. Changed the output of the mag amp. The mag amp thought the line was had an overcurrent position and shut the whole line down. $12,000 a minute for that line not to run. Of course, he hid. The mag amps, there was all the relays was out here, and then it had what we call an access door right here, and then the mag amps were mounted in the back right here. And the dentist was back in here measuring the mag amps. All the foremans came in a door right here, and they was coming down here looking at all the gauges, trying to figure out what happened. Well, shut the line down. Shut the line down. What did the dentist do? He didn't say anything. And they reset the line, and it came back up, and then it stuck out. But so this is something we take for granted in DC and AC and stuff like that the meter has no effect on the circuit. But that is not true. You're putting a resistor in parallel with something. As long as it's a very low resistance, your meter has no. When we get up to this 10 mega ohm resistor, if this has 10 mega ohms, that has 10 mega ohms, then we're going to calculate our current at what? We're going to calculate our current at 5 mega ohms. Because half the current's coming through the meter and half the current's going through that resistor, right? You understand? So when we calculate the current on there, we're going to use 5 mega ohms instead of, and that's pretty much well the resistance of this meter right here. It's about 10 meg. You can measure the resistance of your meter. Just put it on volts, get a watt, get an ohm meter, put it across the leads. Don't hold it or it'll measure you because it's got a real high resistance. And you can measure what loading effect your meter has on the circuit. Now, as long as you're looking at low resistance circuits or low impedance circuits, we can ignore the loading effect of the meter, right? You understand? When you get into a lot of these high resistance circuits, like some of these communication interfaces here, like this guy, you put a regular meter in there, you're going to affect that circuit. But if you know how it's going to affect it, then you know how to compensate for it, right? Does that make sense? So yeah, when we put that 10 mega ohm resistor in there, we'll measure this if y'all want to. But 10 mega ohm will be close enough. We're just not, 5 will be close enough. We're just not going to use 10. And what we're going to do is once we got a reverse bias, we're going to take a soldering iron and bring it up to this thing. And what should we expect the current to do? Should it go up or go down? Huh? When we heat the diode up. I hope not. Yeah, because this is not metal. This is a semiconductor. Most of the time when you heat something up, they become more active, right? That's why we wash it. That's why we wash dishes in hot water. Why? Because the detergent and everything becomes a lot more active. They come move around. So it creates, we've got a reverse bias. What's the current flow going to be consist of? Minority carriers or majority carriers? Reverse bias. Reverse bias. Majority carriers or minority carriers? Minority carriers. What determines the amount of minority carriers? It's temperature, directly controlled by temperature. If we increase it, the atoms get more active, more minority carriers move up into the conduction band, and it's controlled by temperature. The hotter it is, so what we should expect is we have it running, I come over and put a soldering iron across this, we should see the voltage drop across this resistor go up. And then we're going to get a can of free spray. We're going to spray it on there, and we should see it go to almost zero. Because free spray is cold, right? Free spray is something that's a troubleshooting tool that we use. That we spray it, and it's really, really cold. And because a lot of things, they operate when they're cool. and they stop when they get hot. So that's the way we figure out which one of them's doing it, because it's an intermittent problem. And we'll just take this little can of speed spray and do what? Just squirt a little bit on, not a lot, because it causes a lot of condensation. But just squirt a little bit on that, and if it starts working, the last thing we squirted was, what's the problem with getting hot? So freeze spray is a good tool. Don't spray it on your hand, because you get frostbite on it real fast. We used to, when we was in the Navy, when they moved the big old planes around, we had what we call wing walkers. And there was so much noise out on the flight line, we had these air horns. So the wing walkers were out on the wings of the plane, so the tug driver would know if they could clear and stuff like that. And we found out you could turn them upside down and squirt them, and it'd squirt that nothing but solid ice on it. So you'd look around and see where everybody was at, because they'd sneak up behind you, turn it up, and put it up the crotch of your pants and hit that thing. So you always look around. So they had one guy in the back. You had one guy walk behind the tail. You had one guy on each wing of the big old airplane. Then you had one guy in the front that was monitoring everybody else. Then you had the tug driver. Was the big old thing that moved the planes around. So we're gonna be okay. Let me explain one more thing, and then we'll look at lab. So what is the diode lab? Diode characteristics lab. By the way, in this class, these tabs up here, these are our labs. Diode characteristics. Okay, it's because it says, gives us some nice objectives. Then it says we're going to use a 330 ohm resistor, 1 meg. We're not going to do a 1 meg. 1 meg would burn it up. We're going to use a 10 meg. And then we're going to use a 1N914. Now, what we're going to have to do, and this is in my book, so when I give you all the lab procedures, it's going to tell you before you start a lab, what do you need to do? Come up here and do the modifications in your book, because I don't remember all of them, right? You understand? Now, the problem we have with our variable supply is we're going to have to bring this thing down to 0 volts. It's almost impossible for a variable supply to put out 0 volts when you turn it down to minimum. So what are we going to have to do? We talked about that other class. Y'all remember? Nobody remembers. So we got a DC supply. And normally it would be ours. We got a variable supply on our trainers. Everybody's familiar with those. Are you okay? Yes? No? And the minimum we can get out of this thing is around 2 volts. We turn it all the way down. And that's an average. Everybody won't get the same thing. So what we'll do is we'll come over here and we're going to forward bias it. So I'll turn it in that way right there, right? So we'll put this in the plus DC supply. And on this one, we'll hook this over down to ground, right? You understand? And then I'm going to come over here and I'm going to put a 330 ohm resistor. What's the color code for 330 ohm? Most people say black. That's wrong. Black means I add no zeros. We got to add 1 0. Got to add 1 0. I don't know what it is. You know, people see that black and they say, well, black's equal to 0 and I need a 0. But remember, that number is the number of zeros you're going to stick out there. So black says I'm going to put 0 zeros, right? How many do we need to put? Need to put 1. So it's going to be orange, orange, brown, right? Okay. Now, what's the two things resistors are mounted in? I mean, measured in. When we go out and buy resistors, we're going to have the value of them. What's number 2? Their power rating. And this gets to, I think, I taught a class in power supplies. We had these guys actually designing and building their own power supplies. And they were coming up here, and then, but once they got it built, they was trying to do the specs on it, trying to see how good it would regulate, putting different loads on there. and they was supposed to put a 100-ohm resistor over there, and they was burning them things up left and right. And they said, something's wrong with my power supply. It keeps burning up these 100-ohm resistors. Well, what was they doing? They was, yeah, I mean, good gracious, that's putting 30 volts across a 100-ohm resistor. V square over R, right? You understand? And they was using a quarter-watt resistor out there, you know, instead of a 10, 15-watt resistor. They was trying to use a quarter-watt resistor. And the lab, and you got to understand that. So when you buy resistors, not only are you concerned with the value, you're concerned with the power rating on that. So what does it say we need to use here? Does it say? See, yeah, so the book's even screwed. Because it says I need to use a 330-ohm resistor. So we'll need to calculate that. So let's look and see what maximum voltage they're going to ask, right? What's the maximum voltage they got in their table? Yeah, we'll have to calculate that. We'll have to see. Does it say? Because what we're going to do is we're going to measure current. Y'all understand that? We're going to measure current. Everybody understand that? So we're going to measure two things. We're going to measure the VF right here across the diode. And I don't know why to keep. Oh, I know what's going on. I got my string wrapped around my button. We're going to measure the VF of the diode, and then we're going to measure the voltage drop across the resistor. And we're not going to use an ammeter. We've got a resistor. So I'm going to use I of the diode, right, is going to be what? VR divided by R. So we're going to use that 330 ohm resistor to calculate our current. So I think a quarter watt's going to be okay, I think. Now the problem is that I can't put 0 volts across the diode because the minimum I can put would be what? 2 volts. So how would I get 0 volts? Of course you could hook it across there, but how could you get 0.1 volts? So we're going to start off with 450 millivolts, 500 millivolts, 550 millivolts, 600 millivolts, 650, 700, and 750. So it means I got to get this power supply that puts out 2 volts minimum. I'm trying to get 450 millivolts into my circuit. Somebody help me? We're going to put a potential on it. So we're going to come over here, we're going to put a 10K pot right here. Common. This right here is going to feed that right there. So if I adjust my pot down to the bottom, what would it measure? 0. If I adjust it all the way up to there, what would it measure? Well, it measures what we're going to get. We're going to probably put more than 2. We're probably going to have to get more than 2 to get 750 millivolts out. We'll see. It doesn't make any difference. So we might set it to maybe 10 volts. So now I can go from 0 to 10 volts. If I can't get 750 millivolts, I'll turn it up to more than 10 volts. Right? That makes sense. So now I can adjust it from 0 to whatever's required to get all the way up to what? 750 millivolts over here. And that's the last thing they asked for. Their circuit is a little different than ours. Let me hook the circuit up like they have it. I did it out. So what they're going to do is they're going to put the resistor first. So we're going to take the output of our pot. So the pot's real hard to work with. You got 2 leads coming out like this. You got them 3 leads coming out the side. One of them's going to be 1. That's going to be one of these guys. Next is going to be 2. 2 is the wiper. That's going to be the guy in the center. And then 3. And 1 and 2 are, you can interchange them. It don't make any difference. There's a standard, but I don't have it in my head. But it determines which direction you turn it. So that means if I hook it up one way, I might turn it clockwise for the resistance to change it for the voltage to go down. If I hook it up the other clockwise, what causes it to go up, right? Does that make sense? What's very, very important is you take one of the leads that is not the wiper and you connect it to your common. This will be common, right? You understand that. This one right here is going to go back to the V plus output of the trainer. Everybody understand that? Then this, the wiper, this guy right here is going to come over here and do what? It's going to feed the resistor. They have the resistor first in the circuit. Yeah. And then our diode is going to be right there. And it's going to be connected to common. When you measure the input to the circuit, right, you would measure it right there. Not over here. This is not going to change. It's going to be on the wiper or the diode, what's coming into the input of that resistor, right? Measure the voltage drop across the resistor. So what you're going to do is you're going to put a meter right there. So we're going to work in teams of 2, by the way. 1, 2, 3, 4, 5. Somebody's going to work by themselves. So there's 6 in here. So we'll have 3 groups. Okay. So that means everybody should have what? And if you don't have your meter tonight, there's some bench meters over here. Okay. Well, we're going to use our trainers. So the trainers, y'all see the black trainers over here? Y'all be the only ones using it this semester. So when you do on your lab form, when you fill out the equipment that you're using, that has nothing to do with the trainer. You're going to be assigned the trainer. But when you go out and like get an oscilloscope later on, you're going to document the test equipment you get out. And in that way, I'll know who don't put stuff up, right? You understand? So you're not being made responsible for it. Of course, if you go over there and throw it down on the ground, that would upset me a lot. But, so you'll put your meter right here and measure what? VF. You'll come over here and measure VR. What are you going to do with VR? Yeah, you're going to do I of the diode is going to be equal to what? VR divided by 330 ohms. We're not going to measure that. We're going to take for granted it's right. It's going to, even though it might not be exactly 330, it's going to be close enough, and it's still going to do our curve. Our curve will still come out perfect. So this is what we're going to have to do. Do y'all understand that? So set this to probably 10 volts. You're going to have to set it above what's required, right? You understand? So this is why, and that's in the book. So if you want, so here it is. Because you don't measure the resistors. We're not going to measure any values. What are we going to do? We're going to use the color-coded values. And if our calculations don't come up, and that's what you need to start doing. So when you get out in the field and you start troubleshooting, you're not going to go out there and measure all the resistors in an amplifier circuit, right? You understand? What are you going to do? You're going to use the color-coded value. And you understand now that your measurement, your calculations are perfect, and your measurements are not, but they're going to be so close that you'll be able to tell if something's wrong. Right? That makes sense? Now, when we get over to table 31 dash, what's y'all's number, by the way? Is y'all's lab 31?
Yeah.
Okay. Yeah. So when you get over to table 31-3, we're going to do this as a class. It says we're going to go up to, what? 15 volts. This diode's got a breakover voltage of 100 volts. If we put 15 volts across that thing, we wouldn't be able to measure anything across our 10 mega ohm resistor. We're not even close to breakover. So we're going to do 30, 60, and around 100. Greater than 100. It's going to be greater than 100 to break over. And we'll do that in here. We got a stack of power supplies in there, and we'll hook that up and do that as a class. So we probably won't do that tonight, unless everybody gets through, but I don't think we're going to do that. Are we okay? So y'all take a break, then I'll get back and I'll give you all the lab procedures, and then show you all the lab forms. In fact, I didn't run off any lab forms. Dang it, Rich. So y'all need to figure out who y'all going to partner up with. Now, here's the lab form. So I'll run them off for y'all tonight. Then I'll run them on the copy machine for the next class. 1, 2, 3, 4, 5, 6. Thought we had 7 in this class. Huh? There is 7? Oh. Okay. So somebody's going to be by themselves. Y'all figure out who that's going to be. I hate this song. That's Greencast-O-Matic.